In this little lesson, I'm going to review how to use net potential tables and how we can also use table J to answer the same questions. So we get to this question here where it says calculate the net potential of the following reaction. Now in table J, you cannot calculate the net potential. You can tell if it's spontaneous, which means the reaction works, or you can tell it's non-spontaneous, which tells you the reaction does not work from table J. You cannot calculate the net potential, but you can tell me very quickly if in fact it is spontaneous, all right, or not. But quickly, let's figure out the net potential. So when I look at this, I have to figure out the half reactions. Well, I see calcium 0 going to calcium plus 2. Sulfur is negative 2. Standalone silver is 0. Silver only has one oxidation state, plus 1. Now there's 2 of them, so it's plus 2 overall. That means the bottom numbers, of course, have to equal 0, the overall compound. Sulfur is negative 2. To make it 0, negative 2 overall. And assigning oxidation number is the first skill in this process. Now we're going to write half reactions. Take my calcium 0, and it's going to become calcium plus 2. And then I put the 2 electrons on the product side so that both sides have the same charge. A negative 2 and a plus 2 is 0. This side is 0. That's your check. And now I have my silver plus 1, and it goes to silver 0. Now if you notice, my charge is going from plus 1 to 0. My charge is going down, which means I probably, and I'm definitely, adding a negative to that. So I'm adding an electron. Okay. Now, some purists would say, well, you're producing 2 electrons and you're absorbing 1, so you're not balancing the charge. So what I can go ahead and do here, and it doesn't change anything, I can put 2 electrons here, 2 here, and 2 here. It doesn't change anything. Okay, so I'm producing 2 electrons and absorbing 2. Now let's go find the individual oxidation and reduction potentials for these half reactions. Now, I'm going to go find the one that is reducing first. So this is my reduction half reaction, and I know this because the silver plus is gaining 2 electrons. Its charge is going down, and reduction is gaining negative charges. So I'm going to go to table E. A reduction potential table to find. Here I have my reduction potentials at standard conditions. That's why the little 0 is there. This E means electromotive force or voltage for the V, which is the charge per the joule per coulombs. All right. Any case, I'm going to go find silver ions gaining electrons, and there it is. There is my half reaction, and it's positive 80. Now you may say, Mr. Grodsky, we had 2 silver ions with 2 electrons making 2 of these. Wouldn't we double this voltage? And the answer would be no. This voltage never doubles or triples based on the electrons, because electrons is due to amperage, current, how many charge is being passed around. Voltage is the potential for current. It is the pathway based on how well silver, in this case, reduces, and it reduces pretty well. It has a positive 0.80 voltage, so a voltage you would never double by trying to balance the electrons. It is a pathway that's set. Okay, it's a physical intensive property based on how well silver itself can gain electrons, based on its electronegativity and all the other things we've talked about throughout the year. So 0.8 volts is what we need there. So 0.8 volts, I write there, 0.80 volts. And then I find calcium oxidizing, so I go back to the table. And we go find our calcium. Now you notice it's all written as reduction potentials. So calcium plus 2 hates to reduce. Look at this negative voltage, which is non-spontaneous, which means it loves to do what? It loves to oxidize. So I'm looking for calcium to oxidize in my half reaction, so I have to flip the sign. It's positive 2.87 voltage going this way. So I write it positive 2.8, nope, I can do that. Positive 2.87. All right, I can do this. And that is the oxidation potential. Notice I wrote positive. Notice this is what? This is the oxidation half reaction because I'm losing electrons. My charge is going up. Now to find out if this is spontaneous, really based on table, that reduction time, you add these up, of course, a positive and a positive will give you positive, and you get 7, 8 and 6 is 16, and of course you get 3.67 volts. And because it's positive, the cumulative effect of two things that are good at what? In this case, calcium's good at pushing the charge along, and silver plus ions are good at pulling the charge along. So collectively, they create a potential difference. It's very high, 3.7 volts, and is of course very spontaneous. Now, I could have done all of that without doing voltages in terms of just figuring out if it's spontaneous or not. If I go to table, back to the same table, and I notice that my calcium is oxidizing, and that my silver, whoa, way down here, oops, and my silver plus, okay, is getting reduced. Okay, you can look at, I don't know if I can make this smaller, but I will try. You can see that there's an interesting angle here that I like to talk about, where the one who oxidizes is higher than the one who reduces. So the one who oxidizes higher than the one who gets reduced always gives you what? Positive volts. Notice this will be a positive 2.7 and this will be as is. So if you think about it, any of the ones that are high, when they go this way, if they're going to oxidize, you're going to flip all these signs. They're going to be tremendously positive, and that'll be enough to overcome all the other ones. Think about something like magnesium. When it oxidizes, it's positive 0.237. Therefore, it can force something like beryllium, who when reduces is negative 0.17. So magnesium can force something who doesn't what? Pull electrons, or can't gain electrons very well. So a positive 0.237 will what? Overcome any negative below it. So always get the one who oxidizes above the one who reduces in this chart anyway. They'll give you positive volts. Why am I mentioning this? Well, my friends, in chemistry, as we make this bigger, go back to where we were, let's go to table J. Now, table J, of course, as I've talked about, is a terrible, terrible table where they list the metals in their activity series, and they list them based on their ability to oxidize, since metals what? Lose electrons. So they're basically listing these guys based on their ability to oxidize. Now, if you look at lithium, rubidium, okay, you can see that this is essentially the same list that we have here. Lithium, rubidium, I think they switched to cesium, but look at this. We got calcium down here, sodium, magnesium. Let's go look at this list. Now, I probably should be picking the pure metals here. They're listing the metals here. So in any case, let's go to our problem. Let's go to calcium and look at what was the other element, and the other element was silver. So I'm going to make this smaller again because I have to pick an example that's so far away. And our silver is over here. So what did I say? The one who oxidizes is above the one who what? Reduces. This would be also spontaneous. Now, table J, it's terrible because they're leaving out what? They're leaving out the fact that you have what? What? Ag plus an electron making this. And here they're leaving out that this, calcium 0 is made from calcium plus 2 electrons. And what did I circle before? I circled this and I circled this. And we had this nice what? Angle where the oxidizing, or the element that oxidizes, is above the one who reduces. So you can use this table very easily to do the same thing in terms of trying to figure out whether or not it works. The one who oxidizes is the one over the one who reduces, except the one that's reducing is going to usually be in the what? In the form of an ion. So you have to remember that you're assuming, so if I had nickel, if nickel was going to reduce in the presence of calcium, we're not talking about nickel, because nickel, no metal can really reduce. Metals can't lose electrons. Okay, I'm sorry. I'm sorry. Metals can't gain electrons and become negatively charged, but metal ions can. So if we're talking about calcium and nickel, we're really talking about nickel plus 2 gaining 2 electrons, and this would be the angle here. We have to make the assumption with table J that we're talking about the ion form of these metals. So that's how we can use this chart, table J, to figure out just spontaneity. So in number 2, calculate the net potential. You should do those, but to see if something is spontaneous or not, all we got to do is go to table J. So if you notice, who's oxidizing, who's reducing? You might have to do a what? You might have to do a half reaction. Copper plus. From 2 to plus 1, my charge is going down because I gained a negative. Copper plus 2 got reduced. Chromium plus 2 must be getting oxidized into chromium plus 3. This is plus 2. Its charge is going up. Why? Because it's losing an electron. So in this case, very difficult to do this one. Copper plus 2 is gaining an electron. Chromium plus 2 is losing. So you'd have to look for the exact chromium plus 2 to do this. You really can't do this in table J. You can do this on the net potential table. So chromium plus 2. So chromium plus 2 oxidizing is right here, going this way. This becomes positive. And then we had the copper plus 2 reducing. And there it is right here. And as you can see, you get that nice angle, or we get the one that's oxidizing above the one who's getting reduced. You're going to get positive volts. This is positive 0.41 going this way. It's positive 0.34. And to get the net potential, you can just add those together. This question, you needed this table because chromium plus 3 is not listed. Notice I got chromium metal that could oxidize and chromium plus 2. Table J is not that specific if it has chromium in terms of its two different states that could oxidize. Alright, just has chromium. So this one is probably 2. So we can't really use that one. Not really a great example, but I feel bad now I'm over it. These questions are easy to understand because the ones that has the greatest ability to reduce, okay, would again need be on table E. Reducing is gaining electrons, so as written in table E, they'll have the largest positive voltage, okay, as written. And if you can see that F2 on table E is going to be on the bottom, it has the greatest ability to reduce, and that's why F2 wins. Look at this as the largest positive volts for this table. Greatest ability to oxidize would be the one with the largest negative volts on this table because you're going the opposite way and you're looking for a metal that's highest on your table, and rubidium of these choices, nickel, lead, and gold, would be higher. Now, we can look at both tables to answer this, but going to our table here, rubidium of the 4 metals is higher than the other metals listed. And I could do this on table J as well. Rubidium is higher than the other metals, so of course it's better to oxidize than any other listed. Lithium, if it was posted, would win. In the other question, of the nonmetals posted here, fluorine is the best nonmetal. And what do nonmetals do? Nonmetals gain electrons. We talked why. And gaining electrons is, these are the ones reduce the best. So that's why F2 is the answer. So table J could be used to answer those. Don't forget that nonmetals, okay, are gaining electrons. This is listing who's the best at reducing. And which chemical species the most reactive oxidation agents? Agents think opposite. So oxidizing agents themselves get reduced. Who gets reduced the best? F2. That's why choice C is. Okay, on this side, we have some very classic Regents questions. and also questions you'll see in other areas, even AP and or SAT 2. And these questions deal with understanding the reactivity series. So let's get started with which of the following will replace tin in tin chloride. So what they're saying is, how in the world, or which of these elements below will force tin to pop out and be tin zero? Think with me for a second. If tin in tin chloride is what charge? Well, we know each chlorine's -1. There's 2 chlorines, so it's -2 overall. So the overall charge is +2. Each tin is +2. So what we're saying is, who's going to help make tin +2 that's in the compound become tin zero? Well, of course, this is reduction. Its charge is going down because it's gaining 2 electrons. This is reduction. So I need something that's going to force the electrons onto the tin. I need a reducing agent. I need something strong enough acting as a reducing agent. Reducing agent is something opposite that becomes oxidized. So I need something strong enough to help reduce this. I need something that oxidizes enough to force this to happen. So in my reduction potential tables, I can go find this, and I could look for what? Any what? Element or compound that's above it, right? X +2 +2 electrons. We know that whatever is above it is going to oxidize, and whatever is below is going to reduce. That's what we've been dealing with the table that I gave you. The one that oxidizes above the one who reduces will give those positive volts that we get from the reduction potential table. However, in New York State Regents, we don't have reduction potential tables. They have basically taken that table, reduction potentials, and put it into table J, a reactivity series. So we still know who oxidizes should be above the one who reduces. Now that we have established this has to reduce to get out of here, because once it is a zero, it no longer is going to attract the negative here. So we're looking for some element, okay, or chemical species that has a what? That's more reactive in terms of oxidation than tin. Has to be above it. So let's go to table J. Who is above tin? Well, we're looking at lead, titanium, silver, and copper. Find our tin. And there it is. It's listed here. We know better. It really looks like this, doesn't it? Tin +2 +2 electrons gives me that. That's how it's supposed to be, with some kind of voltage here. But we can work with this. Now, so tin is going to get reduced, and the one who oxidizes has to be above it. So what did they give me? They gave me copper. They gave me silver. They gave me lead. And they gave me titanium. Yeah, that's your winner right there. And why is it your winner? Because as I've said before, the one who oxidizes has to be the one over the one who reduces. Now, specifically, tin does not get reduced. As I said before, the only thing that gets oxidized is standalone metal. So tin can't get reduced. It becomes what? Only oxidized. So we're really talking about the tin +2 ions. Since they don't post them, you're just going to have to assume they're there. And if titanium is over tin, that means titanium can what? Be a strong enough reducing agent or get oxidized enough to force tin's reduction. That's how that works. The one that's oxidized over the one that gets reduced. Even though tin's not getting reduced, terrible table, okay, we have to make these assumptions here. Just like our standard cell's not a metal, it's 2 H pluses plus 2 electrons here. So if I ever ask you which of the following metals will produce hydrogen gas, well, all these metals above it can do what? Force the reduction of H plus by being what? Above it. So all of these metals above the H2 could force H plus into accepting electrons or force it to get reduced. That's why these are great reducing agents. But copper and silver and gold, as we've seen today, Cannot. It'll be non-spontaneous. All of this will give us positive volts. This all comes back to positive volts and spontaneity. If the one who oxidizes is above the one who reduces, you get positive volts. Positive volts, which means spontaneous. Back to the... So these get pretty easy. Which metal can reduce strontium plus 2? So we're looking for strontium to get reduced, which means we need to find in that table something above strontium that can force it to get reduced and be a strong enough reducing agent. We need something above it. Okay, so let's go to the table. Okay, let's go find our strontium. There it is, but it's going to get reduced. So what's really getting reduced, as we said before, got to use your imagination here. Strontium plus 2 is going to gain 2 electrons, and it's going to get reduced. I'm looking for something, you bet, something above it. Okay, so my friends in chemistry, the choices they gave us were manganese, 9, copper, okay, which is below manganese, 9, cesium, hey, and of course they gave me nickel, which is below it as well. So the only one that is above it, which means is a good enough at getting oxidized that can force this to get reduced, or a strong enough reducing agent to send its electrons onto it, is cesium. Why? The one who oxidizes above the one who reduces, and cesium's the answer. So cesium's the answer here, and I believe my other answer was my titanium. Okay? All right. Any case, these are all done the same way. You got to figure out, if we're talking about oxidation or reduction. And number 3, which metal will react spontaneously with silver? Like, Mr. Grodsky, is that oxidation or reduction? How do I know? I know how to use table J. It's very simple. What can only metal do? If this is the chemical species that's undergoing redox, what can only metals do? My friends in chemistry, metals can only lose electrons. That's what makes them metals. They're bigger radii, they have ability to lose. So a metal, standalone metal, can only oxidize. So if this is going to oxidize, you're going to pick a metal that's underneath it. Okay, if you go to table J, only gold is underneath. The rest of these are above. So if it's a multiple choice question, it's the one that's different. All right. However, these questions may not be multiple choice. It may be a part 2 question where you have to answer it, so you have to know. So if this is going to oxidize, like we've talked about, the one who's going to reduce is below. Now, is gold going to reduce? No, we know better. It's going to be the what? The Au plus 3, which is a common ion, plus 3 electrons, becomes the gold. That's what's going to reduce, and that's going to force the silver, the Ag, to oxidize, because the silver is above the gold. We're just going to have to use our what? Our imagination to know that really we're talking about silver plus 3, but they'll put that there. It's just a terrible table. All right. And again, which chemical species will oxidize Na to Na plus? Well, if Na is going to oxidize, I'm looking for something to reduce to get positive volts. So I'm looking for an element below it. Okay. Although they're picking the ions now. Okay. It's nice. Even though the ions aren't listed, we have to use our what? Imagination. So these are all done the same way. I want to jump to number 7 because this is a little bit different. Number 7 has no metals. It's a bunch of nonmetals. And if we go to table J, we can see that the nonmetals are listed just like the metals, and they're listed from their ability to reduce the best. So unlike this chart, which shows the metals, their ability to oxidize is on top and their ability drops as you go down, here it's listing as the most reactive species, its ability to gain electrons or reduce. Gaining electrons is reduction. Grrr, okay? So in this table, these rules are flipped. And again, I can't stand these tables, but we have to live with them. So if you have reactions just with these guys, you have to understand the one that's higher is the one that's going to reduce, and the one that's lower is the one that oxidizes. And why? Well, because the one who's better at reducing is going to reduce, and the other one it's not, is being forced to oxidize by the better oxidizing agent, okay, which is who reduces very well. This chart is flipped because the metals who are good at oxidizing will force the reduction of the ions that aren't very good. Here we have the opposite. So if we have F negative, 2F negative, okay, goes to what? F2 with 2 electrons, okay, and it's probably going to be written the other way. It's always written as reduction, so let me try to do this correctly. So 2 electrons plus F2 gives me what? 2F negative. And since this reduces the best, you're going to have the reduction over the oxidation. So back to this question. All right, that's very odd, and you'd never have to do these silly rules if you had net potentials, but we're stuck by it. So let's go back to last. Okay, which species got reduced? Well, we have a 0. We've got a 0 for the iodine. And the question is, who's positive, who's negative? Well, Br2 goes to Br what? Well, there's 2 Brs, but who's better at getting reduced? The Br or the I2? So if we go to the table, we can see that the Br is better at getting reduced than the iodine. So the Br, for this to be spontaneous, Br2 has to get reduced. It's the reduction over the oxidation if you're working on this side of the chart. So Br, for this to work, has to get reduced. So therefore, this gains 2 electrons, right? 1 for each Br. And this becomes 2 Br negative. And then, of course, I2, like ice cream, I2 gets oxidized. Okay, which means it loses electrons, which means 2I plus 2 electrons. The only way that can work. So who got reduced was Br2 because it's better at getting reduced based on that table. But you can see questions where they're going to say, is this spontaneous? Is this reaction spontaneous? And you'd have to know that this guy became negative and this guy became positive for this to work. So table J gets really, really funky and weird and terrible, even worse when it comes to the non-metals. Just be aware of that. Okay, hope that helped. The best there.